Hi, this is part 2 of 2 in a video series on basic DC circuit analysis. In this video, we will see how to construct a basic resistor network on a breadboard, and we will look at how to use a multimeter to detect the voltages and currents flowing through the various components in the resistor network. Prior to viewing this video, you should view the analytical portion in part 1, so you know how we determined how much current and voltage we're expecting to see through and across each of the components. Prior to building the circuit, it's important to understand how a solderless breadboard is configured. In this solderless breadboard, there are vertical connections between each of the holes here in a vertical column. There's an electrical conductor underneath each of these columns so that any component put into any of these holes is electrically connected to all of the other components that may also be inserted into that particular column. Up here at the top we have buses, and these buses behave exactly the opposite way from each of the holes vertically here. They are connected horizontally. Across this trough in the middle, I like to refer to that as the Great Divide. There is no electrical connection across that trough. That allows us, if we're going to put chips that may have pins on both sides, to straddle the trough so that they're not shorted one side relative to the other. So we will use this solderless breadboard as we assemble our circuit. This is a digital multimeter that can be used to measure voltage, current, resistance, and a variety of other electrical properties. You can see on the dial that you can choose what it is you're interested in measuring. In this particular multimeter, we're able to measure AC voltage, DC voltage as indicated AC by the sinusoidal pattern, DC by the flat line. You can also measure DC voltage in millivolts for small signals. You can measure resistance as indicated by the omega here. You can detect diodes, which is beyond the scope of this course, and you can also measure current in milliamps or amps, and in this case microamps for very small current. You can turn this dial to select the appropriate quantity that you're interested in measuring. For example, to measure DC voltage, we can simply turn the dial up here to the V that has a flat line across the top that indicates DC. And then what we can do is we can take these leads over here and we can put them in our circuit where we want to measure one value relative to another. And so the red lead will go where we want to measure relative to the point where we will put the black lead. In order to measure voltage, our red lead must be inserted into this port over here that is labeled with a V. Likewise, if we were to measure resistance, it would need to be in this port with the label of omega. When we're interested in measuring current, we can change the dial over to current, and that also requires that we change where the lead is configured. So we would pull this lead out and put it over here into this port on the multimeter. If you were interested in very small currents, notice that this port is labeled milliamps or microamps, so if you're interested in a small signal, you can measure right there. Different multimeters have different configurations. It's important if you're going to use a multimeter that you read the manual that came with that multimeter so you know whether you have to change leads and what different dial positions or other configurations control different measuring sources. Before we build the circuit, it's important that we understand the resistor color code. So resistors look very similar to one another, but they have very different resistances inside of them. And the way we can tell how much resistance is inside a resistor is based upon the colored stripes on the side of the package. Most resistors that you will see will have a 4-band color code, just like this tan resistor that you see up here. In a 4-band color code system, the first 2 bands indicate the first 2 digits of the resistance value. The 3rd band represents the multiplier, and the 4th band represents a tolerance. So, for example, if we had this first band that is green, then green, if we look down on the chart, represents 5. Our second band here is blue. Blue is 6, so we have 5, 6, or 56 times. Our multiplier here is yellow. So yellow is 4, and we're going to multiply by 10 to the power of 4, or 10,000. So we have 5, 6 times 10,000. So that would be 560 kiloohms of resistance, and that would be the nominal resistance value for that resistor. This last band over here indicates the tolerance of a resistor. And so if you have a brown band, then you can be within 1% of the nominal resistance. If you have a red band, you can be within 2%. If you have a green band, within 0.5%, blue band within 0.25%, violet or purple band within 0.1%, and if you have a gray band, you can be within 0.05%. Typically, the resistors you're going to find in most electronics labs are going to be gold or silver, and that indicates plus or minus 5% or plus or minus 10%. So no electrical component is perfect, so it can vary by up to 10% on the resistance value. And for most components, 10% variance will be okay. For all the circuits that we will build in this particular lab, we're going to be using gold band resistors, which are plus or minus 5%. If you have an important application and you really need tight tolerances, you can get resistances with smaller tolerances, but those are going to cost you more than those resistors that have a larger tolerance. So for our purposes, plus or minus 5% will be perfectly fine. If you do run across any resistors that have 5 colored bands, then they will typically have a blue package as opposed to the tan package that are the 4 color bands. And you will see the first 3 stripes indicate the first 3 digits. The 4th stripe is the multiplier, just like you've seen before. And then the 5th stripe is the tolerance. Before we begin building the circuit, let's recall what the 3 resistor network looks like that we analyzed in part 1. So recall, we have a 5 volt DC power source, DC voltage source, and we determined that it is expected to have 17 milliamps of current flowing through it. We have a 100 ohm resistor that we expect to also have that same 17 milliamps flowing through it, and we expect a voltage drop of 1.7 volts. Over here we have 2 parallel resistors, a 470 ohm resistor and a 330 ohm resistor, both of which we expect to have a voltage drop of 3.3 volts. In the left branch here, the 470 ohm branch, we expect a current of 7 milliamps, and in the 330 ohm branch, we expect a current of 10 milliamps. I've gone on and I have pulled the resistors that I'm going to need out of the bins that we have here in the lab. And let's go ahead and take a look at these resistor values. And let's see if we can determine which one is which using the resistor color code. So if you look here at this resistor, what you will see is it has a brown stripe, a black stripe, and another brown stripe. So if we look back at our resistor color code, what do we see? Brown is 1, black is 0, so our first 2 digits are 1, 0, so 10, and then we have a brown, so 10 times 10 to the 1, that is 100. So this first resistor is our 100 ohm. I'm going to go ahead and put that on top of my schematic right there where I have the 100 ohm resistor labeled. Let's go ahead and look at the next resistor that we have here. And what do we see? This one has yellow, violet, and brown. So yellow is 4, violet is 7, and brown is 1. So 47 times 10 to the 1, that is our 470 ohm resistor. So let's go ahead and put that on top of where our 470 is in the schematic. And now let's look at our final resistor, which should be 330 ohms. Let's go ahead and look at it and make sure we do in fact have orange, orange, brown, which is 3, or 33 times 10 to the 1, 330. So let's go ahead and put that where it belongs on our schematic. And now that we have all of our components identified, let's go ahead and get our breadboard and put these resistors into the appropriate places in the circuit. Now that we've identified all of our resistors, let's go ahead and insert them into the breadboard. To do that, I'm going to pick up the resistor and I'm going to bend the legs over so they're at 90-degree angles, and I will wedge them in to the holes right here. So this first resistor, I'm just going to put somewhat arbitrarily. I want to make sure it's going across this way so it's not shorting itself out. You don't want to turn it vertically because then you're going to short that resistance. And now this will come from here. We're going to eventually put a wire so we can connect to our 5-volt power supply, but we'll ignore that for now. Let's go ahead and get all our resistors into the breadboard. And so we've got our 100 ohm, and now we have this node here where we need to connect the one leg of each of these resistors. So let's go ahead and put one leg from this resistor in, and I'm going to put another one leg from that resistor. Now these two resistances need to be in parallel with one another, so I'm going to bend this on over and put it into another column here, and I need to make sure, since it's in parallel with this other resistor here, that this leg ends up in the same column as I just put that other one down. So I can go ahead and do that and insert that there. Sometimes you'll find that these things don't go in very easily. You can sometimes use needle nose pliers or just wiggle them a little bit to make sure everything is in appropriately. So now we've got all of our resistors, and we need to look at what other connections need to be made. So we've got this resistor going through, that's this right here. Then we've got this node, and that's where all three of these legs are coming together, right there. We've got our 470 coming across, we've got our 330, and they're rejoining over here. And now we need to go back and put in a ground wire or a black wire to indicate the negative side of this voltage source, and we need to put in a red wire to indicate the positive side of the voltage source. Let's go ahead and do that. So I want to use a black wire. I'm just going to cut and have this very short length of wire, about 20 or 22 gauge works well for solderless breadboards. And I've already stripped the ends here, so you can use a wire stripper. If you don't have a wire stripper, you can sometimes use a pocket knife and just strip away the insulation on that. Solid core works best for breadboarding. If you have stranded core wire, you're going to need to twist those strands together, and sometimes it's difficult to get them into a breadboard. So now my black wire is going to come into here. That's going to indicate that this negative portion of the power supply is going to be connected to this node right over here. And my positive portion I'm going to use a red wire for, and that is going to connect right here. So let me go ahead and make sure that's inserted well. Give it enough pressure. You don't have to push too hard, but you do want to make sure the ends of the wires get inserted quite well into the breadboard. And now what I'm going to do is I'm going to use these as lead wires to connect up to my DC power supply. So I have some alligator clips that are connected to banana plugs, and these banana plugs will be inserted into my DC power supply so that I can set up a 5-volt signal for this power source right here. So let me go ahead and clip the red lead to my red wire. That's why we use color codes for our wires, so we know where we need to connect our leads and we know what type of signal is expected on each of those. We expect a ground signal over here on the black. We expect a positive 5 volts signal on the red lead right here. So now we've got that connected. Let's go ahead and connect this up to the DC power supply and configure that for 5 volts. This is our DC power supply that we will use to provide the 5-volt signal used in the circuit. You will notice that I've already inserted the red and black leads into the plus and minus on this 6-volt output. This particular output is configurable for potential up to 6 volts, and since only 5 volts is needed for our circuit, I've chosen to use this 6-volt outlet. Over here, if you needed a larger signal, you can get up to 25 volts over here and negative 25 volts. Let's go ahead and turn on our power supply. So it's turning on, and you will notice by default the output is off. That's very good. You don't want to turn things on before they're configured to the proper voltage. When we are ready to turn things on, we'll just push this output on off, and that will allow us to turn on the power to our circuit. Let's go ahead and press display limit, which will allow us to see what our limits are set at. For right now, we've got a limit of 0 volts and 5 amps. So if you don't do anything, it goes ahead and flashes back. So let's go press display limit again, and let's configure this for our 5 volts. So we can turn this wheel until we get up to 5 volts. And 5 amps is quite a lot of current. So I'm going to press this voltage current button, and I'm going to turn our current limitation way down. I don't expect to have a problem with this, but I want to make sure if there is anything that's going wrong in the circuit that I don't have 5 amps, because that can really actually burn up resistors. That's way too much current for this particular application. So half an amp or 0.5 amps ought to be well more than we're going to see in this particular circuit. If you remember, the currents that we expected were on the order of 17 milliamps. Now that we have our circuit built, let's begin by checking all of the voltages. So I will turn my multimeter up to DC volts. I'm going to go ahead and press the output on/off button on the DC power supply, and I will use these leads to measure the DC voltage between various points. So let's begin by checking what the DC voltage is dropped across this 100 ohm resistor. So I'm going to hold my leads like this, and I'm going to measure from one pin to the other, and I see 1.697 volts. So I'm just going to round that to 1.7 volts, and I'm going to go ahead and label that here. 1.7 volts drop there. Now let's go ahead and measure our voltage drop over here across the 470 ohm resistor. We do have 3.3, and right here across the 330 we also have 3.3. So let's go ahead and record our measured plus minus 3.3 volts. So now I want to measure the current in the circuit. I'm going to make sure, since I'm measuring current on the order of milliamps, that I've switched this lead into the milliamp port, and I've switched my dial over to milliamps. You'll notice on this particular multimeter that the milliamps has this little sine wave over top of it. That means by default it's expecting to measure AC. Over here, this yellow indicates that in order to measure DC, I have to push this yellow button, and now DC appears up on the display. So we're going to make sure we're measuring in milliamps and in DC, and we're going to go ahead and check our current. We've broken the circuit. We're going to insert the leads of the multimeter into the circuit to complete it, and we have connected from here up through here. Try not to touch the lead, but you can touch the resistor. We have 17.06 milliamps. So that is the current coming through this resistor, 17.06. Okay. Now we're going to go ahead and turn off the power again. I've done that off screen. So the power is turned off. I'm going to put this resistor back in place, and I'm going to break my circuit here and pull up the 470 ohm resistor, and I'm going to try to measure the current through that 470 ohm resistor. So now I'm going to connect from that node right here in the middle to the lead of the 470 ohm resistor. That's going to complete the circuit there, and that will allow us to measure that current. So let's go ahead and turn on the power. I've done that off screen, and so I'm measuring from this node up through here. Alright, and what we are seeing is, notice it says negative 7.07. That's because I've got my leads backwards. So if you see a negative value, you can just switch your leads. So going from positive to negative, we're going to go over here, and we're going to see 7.08 milliamps. So let's go ahead and record that on our schematic. 7.08 milliamps. And now I'm going to turn the power off again. I've done that off screen. And go ahead and put this resistor back where it was before. So I've inserted that back in. And now I'm going to pull out the 330 ohm resistor. And now I'm going to do the exact opposite. Just measure the current from here through that 330 ohm resistor. Make sure you don't pull out both leads when you do that. So let's go ahead and turn the power back on again. There it goes. And I'm measuring from here through here. And what do we see? 10.05 milliamps. Let's go ahead and record that. Alright, now let's go ahead and compare our values that we've measured to the theoretical values. In these two diagrams, you will see our theoretical values as well as our measured values. So, in terms of voltage, what did we expect to see? 1.7 volts, 3.3 volts. What did we measure? 1.7 volts, 3.3 volts. So our voltage checks out quite well. Now let's look at our currents. We expected 17 milliamps, and we expected 7 milliamps and 10 milliamps. And what did we see? 17.06 milliamps, 7.08 milliamps, and 10.05 milliamps. So our recorded measured values are very close to our theoretical. And that shows that even with some tolerances on our components, we are seeing currents and voltages very close to what we expect. You can use the techniques presented in this video to help you to debug a variety of circuits. So if you're having trouble building a circuit, or you're not sure why you're not getting a particular current, or a signal's not coming through, you can use a multimeter to detect the voltage and the current in various portions of the circuit, so you can determine where you're having a problem. This concludes part 2 of the video.